do with remote material. What you guys should see on the board at home and here is some problems I thought might be good ones to do in various assignments. I've only posted a place to put the homework up to section 6, as you know. And so I thought you might maybe include everything once I make a place, the rest of chapter 2 in one place. And then I can make individual places here or whatever for 3. But anyway, that's one thing to talk about. Second thing to talk about is the exam, and I'd like to wait until the other 2 people get here for that. So I think we'll go ahead and talk about what's over here on the other board. When you get to section 2.8, and I hope you always look at it, but when you look at the exercises, and I find the place, the exercise problem 1 and 2 and 2.8 have you do something, and it comes from the author talking on page 84, and he says, what we're going to do is solve the following differential equation. This is not a new thing, except he's going to assume that we are going through the origin. Now, what he says in the paragraph before the theorem is 2.8.1. And the theorems are about existence and uniqueness of solutions. Anyway, he says, first of all, we note that it is sufficient to consider the problem in which the initial point is at the origin. In other words, he wants to solve, given a theorem about solutions. And he says it is sufficient to consider this problem. Okay? Now, if some other initial point is given, like my picture here, suppose that the problem is given some other point instead of, don't worry about S and stuff here yet, but he's saying he wants to solve it going through the origin. If instead somebody says they want to solve it going through here, this is what he's talking about. So if some other initial point is given, comma, then we can always make a preliminary change of variables corresponding to a translation of the coordinate axes. This will take the given point to the origin. The existence and uniqueness theorem can now be stated in the following way. Well, my point is, if he's talking to another professor, he can say, we only need to state the condition for this because everybody's smart enough to understand that if it's someplace else, we can translate. We can do what's called a rigid transformation. Well, unfortunately, in our class and in Calc 1 and Calc 2 and stuff that you guys have had, we've never talked about rigid transformations. At least I haven't. And I got one more person coming in. So that's going to be almost everybody. What did you do?
I muted that one, so there's less echo.
I'm sorry?
I muted that one, so there's less echo.
Oh, it wasn't muted? That's because it went off.
Yep.
Yeah, it was all fixed and then it went out. Yeah, thank you.
You're welcome.
Yeah, okay, so we almost have everybody. So whenever we get everybody, if we do, we'll talk about tests. And if we don't, we'll talk about it anyway a little bit later. Okay, so the author just says, hey, we can do this. So fine, probably if you read through these pages and stuff, you might not have even studied that part. You might not, oh yeah, sure, he says we can do it, and everybody, yeah. Okay, problem 1, okay, in page 90, he gives you a differential equation. So he says in problem 1, dy dt, he says, is t squared plus y squared. And he says y of 2, I think, no, y of 1 is 2. For those of you who have your books open and stuff, it's page 90. So he just says, here's a problem, okay? And what does he say? Transform the given problem into an equivalent problem with initial point at the origin. Okay? So he wants us to change the differential equation to solve a different differential equation where the initial conditions through the origin, but he has not provided any way to do that other than he says, just do a translation of the axes and you can do it. So now, maybe you guys are, well, I'm sure you're much smarter than me, but when I start to do that, I think, I don't know how to do that. Nobody's ever told me how to do that. Maybe you guys will think that's easy. I don't think that's so easy. Now, I don't mean that the answer is not easy. I mean, when I'm staring at the problem, I don't know if I myself think it's easy. Do you kind of understand? So, anybody worked that problem yet? It's in section 2.8. Nobody's worked it yet? Okay, well, I thought I would try to show you what the author means when he says you can translate it. Okay, so now the translation from one place to another, an interesting thing that will hit you, I hope, is we're not going to translate it to somewhere, we're going to translate it from somewhere. In other words, we're going to make a function that goes from what we want to have to what we got, instead of taking something from what we got to what we want to have. Is that okay? And so basically the transformation is easy enough. If I have two variables, I just basically transform them by literally adding something or subtracting something from each one. And if I want for 0, 0 to go to T naught, Y naught, that's pretty easy. You just write in those things. And this transformation, it's a function from two variables to two variables. We haven't studied that if you haven't had Calc 3. All right. It's a linear transformation for those of you who have had Calc 3. All right. There's a matrix involved with this. And it actually moves everything over to the right and up. Now, you've done that kind of thing in algebra and stuff earlier when you just want to take a graph and move it up or down or shift it over. You've done that kind of thing, but when you did that, you weren't transforming the whole plane to another plane, okay? Because you wanted to graph the new thing on top of the old thing. And so you wanted to see the new one being up above the old one or over to the right or left of the old one. All right, what we're doing is talking about two different worlds, okay? Where one is just shifted, okay? But the differential equation is going to change, okay? And so this is the transformation that does it. That doesn't help us figure out what to do with the differential equation. I mean, it does, but again, if you've never thought about this, it's like, okay, that's fine, but what do I do now? Okay, well, here's what we do. So I've already sort of indicated, but we let S be T minus T naught. Whatever the T naught is, I'm going to define that. And that also, by the way, says T is S plus T naught. I mean, if you have this, you have that, and that's what I put up there, but we'll see that. And I define a new function W to be Y of S plus T naught minus Y naught. Now, if I differentiate W at S, this is now a function of S over here. Y naught's a number. Y is a composition. So when I differentiate, I get Y prime of S plus T naught times the derivative with respect to S, which is 1. And so the point is that the derivative of W at S is the same as the derivative of Y, same slope. And that's because when I find a solution, suppose the solution looks like this. Okay, suppose when we solve this problem directly, not the way we're going to do it, but suppose you have this problem and you solve it and you get an answer, and the answer is a function. Okay, what we're talking about here is there will be another answer over in this world that goes through the origin. And the point is, if we had the things superimposed on each other, they'd be parallel. Okay, because all we're doing is moving something. And so what we want to do is solve a differential equation here. But when we get done, we want to be able to translate it back over to here. So this is the initial problem. We're going to translate it back, solve it over here. Then at the end, move it back over. And that's a little bit like integration by substitution, where you substitute, you go through the thing, and after the bottom, you substitute back. Okay? And by the way, actually, when you do integration by substitution, you are in two different worlds, but it's just not emphasized when you're learning it. Okay, so we have the left-hand side, and by the way, s plus t naught, that's just t. So w prime of s is y prime of t. Y prime of t is what we're starting with. So I didn't write it. So let me say y prime is supposed to be, well, it is here. This is the left-hand side and the right-hand side. And so if I write it this way, it's t squared plus y squared is the same. Anyway, don't need to write it twice. Okay, so what we do is we solve the following differential equation. W prime of s is f of s plus t naught, w of s plus y naught. Now, that's because the general equation looks like, as you know, looks like this. And so what you do if you have a general equation, whatever it is, you stick, instead of t, you stick s plus t naught, and instead of y, you do ws plus, it just goes along with what I've said here. Okay, and this is actually what you solve. So what is the problem we have right now? Well, f of ty is t squared plus y squared. So what do we actually solve? Well, if f of ty is t squared plus y squared, then f of s plus t naught is s plus t naught squared plus w of s plus y naught squared. That's in general. Now, in this problem, t naught is 1, and s naught, or y naught, is 2. So the problem we solve, this room here, I guess, the differential equation you solve here is s plus 1 squared and w of s minus or plus 2, I guess, squared. This is the differential equation that you solve. And if you do that, I'm running out of room here, but w of 0 will be 0. And so you solve this equation. So anyway, this isn't complicated. The space I have here sort of makes it look complicated. But if you copy this down, or if you read it off the board later when you watch the video, this is what you do in problems 1 and 2. One of the things I wanted you to do is problem 1 and 2. These problems take about a minute apiece once you see how to do it. It's just a copy. Basically, you start out with t squared plus y squared. You change that to s plus 1 squared plus, instead of y, w plus 2 squared, and it's easy. Okay? So the author assumes you knew that. I don't. Now, the other problems, 3, 4, 5, and 10, they take a little bit of work, different work, but I'm hoping you do that. And one of you, I don't know, asked me to give out some problems. And so I forget which person did that. I didn't answer your email, but hopefully you're here today. And this is what I asked. I don't know who asked me. Did you ask me? Yeah, I thought so. Yeah. So this is a start. I'm going to put more. I'll put this on Blackboard as well.
Okay.
Okay, so that's one thing I want to talk about. And the next thing to talk about is what we still don't have everybody here.
I have a question.
Yes, sir.
If you're waiting on Murphy, Murphy's not gonna be here.
I'm sorry.
Murphy?
Yes, he's gone this week, isn't he? Yeah.
Yeah.
Okay,
I'm
good.
just
We don't
saying.
have to wait. I can talk and he can watch the video.
Yeah.
Okay, let's talk about the test real quick. First, we're going to omit on the test, the stuff about difference equation because we just haven't had time to do that. I want to have a test. I want to talk about that. Hopefully we can do it before the end of the semester. Don't know. All right, because we're going too slow right now. I may not feel that way, but that's the way it is in terms of getting done without hurrying too much at the end. So that's section 2.9. Okay. Now, I want you to do these homework problems in 2.10 and 2.8 and so forth. But again, on the test, as far as these sections go, 8, 9, and so forth, and 7, let's talk about 7 first. 7 is the Euler business. I'm not going to ask you any questions about the Euler business because that's really a calculator thing. And I hope if you do these problems, like problem 1 in 2.7, if you do that for homework, that's enough because basically what you would do on a test is just a repeat of this. Okay, it's the same thing you do, and you. I don't have any room here unless I erase this over here. As I think you may remember, it's an easy idea, and that is you have an initial condition, you figure a slope, you do a little bit of a thing here, and then you figure this, and you figure a slope, and so on. And it's tedious, but I think it's kind of easy to see how you build a piecewise solution. It's not a solution at all, but it follows the solution. And that's kind of enough for us right now, because we can't really prove anything with this. Now, by the way, I'm making up some notes to do a proof. And I was going to hand them to you the other day, and I read them again. I thought they won't understand that. So I'm going in and putting more stuff in to try to make it more understandable. And I looked at it last night. I thought they won't understand that yet either. So I'm not done yet trying to broaden the thing so you get some feeling about what's going on. Okay, because there's about 5 or 6 concepts that none of you have had, and so you got to kind of explain those a little bit. And that's what when I read it, I think that's not good. All we're going to do is look at that and say, I have a bird. I'll put this under the bird cage for the bird's droppings, and that'll be its usefulness anyway. Okay, so as far as, so we've just talked about this one. I'm not going to have that on the test. What about 2.8? I would like you to look at the idea of changing things to an integral equation and developing, like I did the other day. If you remember, you guess the first answer, which is usually 0, and you stick that in an integral, and you integrate, and you get a function. You stick that function back in the integral, you integrate again, you get a function. I might ask you some question about that, because that's what you do in terms of proving some stuff. And so we're not asking you to prove it, but if you do a problem like that, you'll understand. And the one we did the other day, I think came out e to the t squared minus 1. What you get is an infinite series. And so you basically, what you do in a problem is create the first 3 or 4 things in an infinite series. And hopefully you can guess what the rest of it would look like if you did it 5, 6, 7, 8, 9. And then you solve the problem independently, and then you say, oh, that's what it is. All right. You could have a question like that on the test. All right. 9, we're going to skip. 2.10, in the homework, I wanted you to do 10 problems. And the reason what I'm calling 2.10, the author calls review. So I shouldn't call it 2.10, I ought to call it review. If you remember on Monday, we talked about Riccati equation. And what if one of the variables is missing, like the y is missing or the y prime is missing? Those are at the end of that review section. Okay, so I might ask you a question to solve one of those kind. That's on page 101, I believe. So in terms of that, now the rest of these, as far as homework goes, if you these problems are good to review for a test because you don't know what section they came out of. And so if you look at the problems in the review, you'll have a list of them. Some of them will be separable, some of them will be linear, some of them will be exact, and you won't know what it is, and that's just like a test. So the reason I assign those is kind of like preparing for a test. Now, when you get to these are the Riccati and the other ones. So the test question might come from some of these, or I might take some problems right out of here because you got a chance to maybe do them. Okay, so that's like the stuff that we haven't had a chance to talk about. And I'm sorry, it's just the way that it is. It makes me angry. We haven't had more chance to talk about this stuff. Anyway, what else is in the chapter? The chapters 1 through 6. There was one section of theory that gave you 2 theory questions about existence. And I want you to know what those theorems say, and the answer, the problems in that section ask you like how wide an interval as the solution exists and stuff. If it's a linear equation, it's as long as the coefficient functions are continuous. If it's a nonlinear function, then you don't know, it's just more local. And you have to look and sort of see something about the solutions. Anyway, you need to look at that. But what was first section? Separable, right? And then linear. Or do we do linear and separable? I don't know which way is which, but anyway, there's linear and separable at the beginning. Then there was a little theory section, 2.2.4 or something. There were 2 theorems, 4.1 and 4.2, something like that. Then exactness. And also in one of the exercise sections was the Bernoulli equation. And so what I would do, what I plan to do for the test is give you 4 or 5 differential equations to solve. And maybe ask you some question like, is this linear? Is this exact? Is this separable? I mean, in other words, give you a problem and say, okay, what kind of problem function is this? And give you a choice of things to say, which would not be a do it problem, it would just be identify it type of problem. The other thing, remember we had chapter 1 in here, so I might ask you to do a direction field. And it would be kind of sloppy direction field because I'm not trying to get you to put it on a machine and stuff, but a direction field. So there might be a direction field in the test. There might be some question about identifying what kind of function we have. I mean, what not a function, what kind of equation we have. And then there will be a few problems where you solve. So I might give you a separable one. I might give you a linear one. I might give you an exact one. Okay, and that's what it would basically, the test would be. Now, I would like to make the test closed book, closed notes, closed friends, no cheating. It's where I would give you a test. You can spend as long as you want to within the time frame where you do the test, meaning you could look at the test on one day, do 2 problems. Suppose there's 5 problems. I'm just making that up now. Do 2 problems one day, go to bed, get up the next day, do 3 more. The point is, in between, you wouldn't be looking at chapter 2 or chapter 1. If that makes any sense. That's not saying you can't open your book because you also got chapter 3. But it would be, you're not going to go back and say, oh, what was separable? Now, the question is, can I trust you? I doubt it, but I'd like to think I can. So they are building a execution platform out on the middle of campus. So if we do have this kind of closed thing and we catch anybody, then we're going to march you over to the place and sort of have a 12th century sort of festival. I'm joking, of course, it's on camera, it's on recorded now. That's a big joke, camera. We're not going to do that. We won't do anything more than take somebody's hand. Okay. So no, all I'm trying to say is please don't, if we do this, don't cheat. It doesn't help you. I'll give you all A's if that's what you have to have. Okay. But getting them by cheating is just not the right answer. Now, maybe you don't want to do that. Okay. If you have an open book test, it will be harder just because you've got the ability to look at everything and redo the thing and all of that. So what do you think? So I'm planning to cheat. So this is a great idea. Let's have a closed book test. I hope that's not what anybody's thinking. So what are you thinking? Closed, open, what do you think? No, the other problem, how long do you have? You know, adequate amount of time, like 15 minutes. No, I can't even write your name in that time, right? So my idea would be to give you the test, give you several days to do it. If we do that, when would we have a deadline? Again, this is best for you, not best for me. If we delay too long, you won't look at the next chapter, then you'll be way behind. Okay. So are you ready to take the test for tomorrow? I doubt it. Anyway, this weekend, first part of the week, 6 weeks from now. Anybody want to say anything?
I think over the weekend would be good. I don't know.
When? Weekend?
Over the weekend, I don't know.
I was gonna say the start of next week would probably be better. for
Yeah,
me.
maybe start over the weekend.
Everybody now talking at once.
Start of next week would be best for me, so,
Starting in part of the next week.
yeah, like get it on Sunday night and then work till like Tuesday or something, or Monday. I don't know.
Okay, so you do the test when? Monday, Tuesday,
Yeah, essentially.
Monday?
That sounds good. I was just saying something.
Okay, so when would you like me to have the test available? Suppose we say it's due next, I don't know, Monday night, Tuesday night, I don't know. Would Monday night give you enough time?
Probably Tuesday.
Tuesday, okay. Tuesday noon, Tuesday midnight.
Midnight.
Midnight, okay. So the test is due, you guys at home are supposed to talk about this, you know. So we'll have the test due Tuesday midnight. Now remember, Blackboard will accept tests late. It just says they're late. Okay, so they will take that. So don't just sweat it if it's 59 after and you still got one problem to do. On the other hand, you should not get in that situation. Okay, but it's not like you have to do it by that moment. But I will see that you're late. Okay, and I might decide to say that's bad. Anyway, okay, when would you like it to be listed? Tonight, tomorrow, Friday, Saturday?
Sunday?
What?
Sunday?
Sunday?
Maybe?
Okay, so anybody at home want to do it tomorrow? Softly. I've already.
No.
I you can hear me.
Yeah.
You may be in the bathroom or someplace down the hall not listening. I understand that.
Oh, I'm listening. I'm listening.
I'm happy about that. Okay, so Sunday night, sometime I'll post it.
Sounds good.
Is that okay?
Yep.
All right, so quit worried about that. All right, let's talk about chapter 3. Okay, because I want to do something, or have you do something that I think is very important. But before we do it, we've got to review section 1, which just basically gives us an idea. So now, if I have a problem like this to solve, or if I have a problem like, I don't know, this is one that's in the book. Okay, And these are just equations now. Now, what we're normally going to do is solve initial value problems, which mean we're going to have initial conditions as well. So we're going to want a unique solution, okay? And I'm gonna get rid of my people here so I can see myself here. Not that I like to do that, but okay. The problem is to find two solutions, which we're later going to call fundamental or independent solutions. We want to find two solutions of a certain type, and we're going to have ways to classify them later. Right now, we just like to find two solutions. And so where we are kind of, at least if it's a couple of days ago when we first started this, it's like x squared equals 4, solve it. And you just have to figure out, and maybe you guess, that's one answer, way to do it. Guess the answers, 2, 5, 6, try different things and see if they work, okay? That's if you don't have any theory. If you have some theory, you might say, well, if x squared equals 4, then I can write x squared minus 4 equals 0, and I can factor x plus 2 times x minus 2 equals 0. Then I remember if the product of two numbers is 0, one of them has to be 0. It's either x plus 2 is 0 or x minus 2 is 0. So either x is 2 or x is minus 2. And I actually solve the problem by some theoretical thought. Okay? Now, we want to do the same thing, except our answers are functions, not numbers. All right? So we want to find two functions that solve the problem. So if I do this problem, if I start guessing, okay, well, what people did, and by the way, this is actually much different than that one over there. And this one, if you copied this one, I'm going to change it. This is not what we're going to be solving. If you look at this one, something's missing. Namely, there's no y prime. So what does this do? This throws us back to chapter 1, page 101, where we had a way of solving the differential equation of second order if one of these things is missing. Over here, it's not missing. Here it's missing. So this is not this chapter. Okay? This chapter would be where I have actually all of those. So I wanted to do that because not always do we use chapter 2 methods. The thing I had a minute ago, we actually will use a chapter 1 method. Okay, now I have this. Okay, so I've got to do something now. I've got to differentiate something twice and differentiate it once and stuff. So when I start thinking about that, to have an answer here, in order, if this is like a sine function as a solution, then the second derivative would be minus the sine function, but the first derivative would be a cosine function. And so if I tried to guess a sine function as an answer, I'd have minus the sine plus 5 times the cosine, and over here would be plus 6 times the sine, with the 6 sines, and the minus sign would be 5 sines, but I got sines and cosines here, and that doesn't equal 0. Okay? And so if we just started guessing, like when I had x squared equals 4, and I guessed 2 or I guessed 5, you know, x squared equals 4, guess 1, it doesn't work. Guess 5, doesn't work. Sooner or later, you hit the right one. Okay. Well, if I just try things I know here, if I tried x squared, what happens? Well, after a couple of derivatives, I get 2x for the first derivative and 2 for the second derivative. Over here, I have 5 times 2x, and over here, I have 6x squared. And, you know, if this was an attempt at an answer, is this equal to 0? Now, what it means is this has to be the 0 function, not just can I solve it and find a place where it's 0. When I'm getting a function, this would have to be 0 period for every x. And it's not. It's only 0 for 2 x's. Therefore, this is not a solution. And if you just start guessing, after a while, it hits you to try e to the something, RT. And if you try this and you differentiate it once, you get r e to the RT. If you differentiate it twice, you get r squared e to the RT. And if I put those 3 things in the original problem, I will have r squared plus 5r plus 6 e to the RT, because I factored out the common thing in all three places. Now, e to the RT is never 0, meaning for any t, not 0. And that means, again, the product of two things is 0. One of them has to be 0. All right. This one is not 0. One of them has to be 0. That means the other one's 0. So what comes out of this guess is that r squared, the r I pick, has to solve this quadratic equation. And it's an equation that's easy to solve. I get r equals 2 and r equals 3. So I get two solutions out of here, e to the 2t and e to the 3t. Now, I'm only looking for two solutions, so I found two, so I'm happy. Except a little more thought. You'll find out that, well, 2 e to the 2t also works, because if e to the 2t works and instead I use this, what happens when I differentiate this? The 2 is a constant. It just stays there. So if I differentiate this once, I get 2r e to the RT. If I differentiate it twice, I get 2r squared e to the RT. And notice that if I put these things in the equation, I have 2, 2, 2 across the board. And that doesn't change the answer. And so now I got too many answers, because 2 e to the 2t is an answer, and 12 e to the 2t is answer, and so on. And what happens if I put an A here and a B here, both of these infinite number of solutions is a solution, but they all follow two patterns. And so if I could develop a criteria to determine that these are different in some sense, I'm looking for two classes of answers, not two answers. The algebra problem is looking for two numbers. In a differential equation world, I'm looking for two basic things. Okay, and it turns out, and I'm going to now talk about something different for a minute. If we have a function, and we'll talk about what x and y are after a while. If I have a function which allows me to take whatever this function does, if I take the sum of two things instead, if I took them individually and added later. Now, this addition and this addition are not the same addition. Because this is a world of adding x and y. This is a world of adding L of x and L of y. And if I'm in a different world, addition may not mean the same thing. But if a function satisfies this property, it's called additive. A-D-D-I-T-I-V-E. And if it satisfies this property, now, what we're doing here is trying to differentiate it between whatever the x is and whatever the alpha is. So in the latter part of Calc 2 or Calc 3, first part, we talk about vectors. And when I talk about vectors, I put lines under the vector. And I talk about scalars, and scalars would be real numbers. So if we were talking about things in Calc 2 or Calc 3, we talk about transforming something, and I could think of the following idea. I could think of L as differentiating, and I could think of x and y as functions. Is the derivative of the sum of functions the sum of derivatives? The answer is yes. So the concept of differentiation is additive. If it is a derivative of a number times a function equal to the number times the derivative of the function, the answer is yes. So differentiating is what we call these two things. The second thing is called homogeneous, and this is the third use of that word in the last few days. Remember, we had homogeneous equations in first order. I told you if I have a 0 here in the second order, it's homogeneous. And now we're talking about a third use of the word for a function that has the ability to take out things is called homogeneous. And when you put the two ideas together outside of Russia, you get linear. Russia has a different definition, but anyway, you get linear. I want to say that about Russia. If you ever read Russia, Russian mathematicians have written some very, very good books, and they translate them to English. And you might go to the library sometime and look at one that turns out it's from the Russian. And the point is that linear is different than the American linear. So be careful when you read translations of books because they may not mean the same thing. What you always have to do at the beginning of the book is check what the definitions are so that you don't just look at something at the end of the book and think it's the same as something else. That's another, but you haven't worried too much about that yet, I know in life, but you will one of these days, hopefully. Anyway, we have linear transformation. What about integration? Is the integral the sum of integrals? Is the integral of something times a function the something times the integral? Yeah, integration is also a linear process, okay? Except a function now is not a function of numbers, it's a function of functions, okay? And so it turns out that what we can do with this equation is make a function out of it. And what I'm writing right here is a function. And if I say equal to that, I'm writing this as a function. Okay? It's a function of t because if I put t here, I'd have to put t every place where it is. And now I have a function of t. And so this function L of y takes numbers to numbers. But L takes functions to functions. Just like integration and differentiation. Okay? And the point is that these answers to the differential equation turn out to make what's called a vector space. Now, vectors to you guys might mean arrows. What do you do with vectors in the plane? You add them and you get a parallelogram. You get a diagonal. When you add two vectors in arrows, you get a diagonal of the parallelogram as the answer to the adding them. If you multiply a vector by a number, you either lengthen it or shorten it, or maybe turn it up the other way if you multiply by a negative number. It makes up a vector space. Supposedly if you had Calc 2, you looked into that. Certainly if you had Calc 3, you're supposed to have looked into that, or if you look at linear algebra, you're supposed to look into that. Some of you had those courses. Anyway, a vector space you think of as arrows. Now, but what you really have is a set of which you have an operation, a function, and the function is additive and homogeneous. And there are properties. And so you can have a world of functions in which you define how to add functions and you define how to multiply them by numbers. We've already done that in algebra in high school. You didn't call it in the thing, but it was a vector space. And the solutions to differential equations turn out to be members of a vector space. Now, if you remember 1, and 01 for arrows, okay, every other vector in this world can be written as a number times 10 plus another number times 01. Like if you have the number 2, 3, that's 2 times 10 and 3 times 01 added up, and that gives you the point. Okay. So these two things are called a basis. Now, but that's not yet why. You need two things for a basis. You need them to be what's called linearly independent. And for arrows, that means they don't point in the same or opposite direction. It means they have different directions. And they need to do what we call span the space. And that means everything in the world is obtainable by multiplying one of those things by one number and another one by another number and adding them. When I write down alpha x plus beta y, that's called a linear combination of the vectors x and y. So when I write down A e to the 2t plus B e to the 3t, that's called a linear combination of the two functions, e to the 2t and e to the 3t. Okay? So it turns out that we're dealing with vector space things. And what we have to define is what do we mean? Like 10 and 01, okay? Those make up all the vectors, and you can't use, no multiple of 10 will give you 01. They're independent of each other. Well, we have to figure out how do these two vectors, e to the 2t and e to the 3t, what makes them independent in the vector space world that they live in? And we'll do that. And then linear combinations give us answers. Another problem is that, are there any other answers besides those? We got these two answers by guessing. Are there any others? Now, if you look over here, if I do the same game and put e to the RT in here, you'll get r squared plus 2r plus 1 equals 0. And that gives us r plus 1 squared. And so I get two answers, -1 and -1. What's wrong with that? The answer to the problem is e to the minus t. Twice. But that's not two different answers. You understand? This equation only has one answer twice. That doesn't give me two independent answers because of the same answer. So this problem is harder than this problem because I'm looking for two answers to base things on. I can find two answers by solving this quadratic equation right here. And I get two different answers. They will satisfy what we need. That's section 1 in the book. However, you can have other quadratic equations that only have one answer. That's a problem because I want two answers. And we can have another problem. I can have y double prime plus y prime plus y equals 0. And when I do r squared plus r plus 1 equals 0, I'm going to get two complex answers. Well, that's no good. I want real answers. Now, it turns out to be very good, but we got to explain why in a little while. Okay, so section 1 is dealing with solving a quadratic equation with two different answers. Section 3 in the book has to do with dealing with things when you have complex answers. And section 4 in the book has to do with dealing with problems when you have one answer. How do you get a second one? Okay, and those are all when the right-hand side is 0. The section after that puts something else on the right-hand side, some other function, and then we have to worry about how to solve those problems. And the way we'll solve those problems, we'll find out, is to solve the one we've just been solving. And that'll give us some things. And then we find one way to solve something where it's not 0. And then we'll put together the two different answers to get an answer in general. But that's way ahead of us right now. Okay. So what's in between? I skipped section 2. Section 2, what I want you to do is 19 after. And unfortunately, I'd like to go another hour here. You might not like it, but I would. Section 2 in the book is very important, okay? And what I would like you to do is, it has, I think, 9 or 10 theorems. Now, I hear groans. I don't really hear groans, but I think I hear them in my head. There's 7, sorry, not 10. That's easy. 7 theorems. Now, the good news is they're all easy theorems, meaning they're not like, oh, crazy things that you can't understand. I think you should copy each one of these theorems down and in your own words. Now, not too much in your own words because you might miss something. But I think you should put down what are the hypotheses to each theorem what are they saying, and what's the conclusion? Now, if you can, I'd also title the theorem. Now, theorem 1, again, run out of time here. Theorem 3.2.1 says existence and uniqueness theorem. Now, the name of that tells me what the theorem's about. What do I have to put in there? I have to put in what are the hypotheses so I get existence and uniqueness. Okay? And if you will write that out for yourself and think about it, it's not difficult, but you'll learn. Now, if you read the paragraphs in between the theorems, the author is telling you what you're supposed to think. But what I'd suggest you do is not read all the stuff at the beginning, is look at the statement of the theorem and see if you can understand what it's saying. Then read what the author says in between, okay? Now, if there's any concept that he brings up that's in the theorem that he explains in the paragraphs, of course you have to read the paragraph first. I'm going to stop the recording here because we're past time.